So we have two tests that we'll be deciding on, we'll be talking about today. One is called the one sample proportion test, and the second one is a two sample proportion test. So that's pretty evident from the names what we're talking about. Discrete data can be of different types. Here we are talking about data wherein we have the proportions in place. So you have a single sample here, it's a one sample, and so we require to make a hypothesis to be able to come to any conclusion for the data. Null hypothesis and alternate hypothesis. These are the two hypotheses that we require to make in any of these analysis wherein we want to either prove or disprove something. Null hypothesis is that hypothesis, a condition which would normally exist. So herein, if you're talking about a certain target which is normal, then being able to meet that target is the null hypothesis. Not being able to meet the target is the alternative hypothesis. So here we have a solved example over here. We have a problem statement. So you have a Six Sigma project lead who wants to determine if a bank's customer satisfaction rating is the same as the national average of 85%. So the point is the national average is 85%. A random sample of 500 bank A's customer was sent a survey. Out of 500, 400 were satisfied. All right. So yeah, so here we have a pointer which is telling me to highlight the point same. Okay. So problem summary. So you have the Six Sigma project lead who performs a one proportion test. Why a one proportion test? Because there is only one sample which has been tested out of the bank's total population, which is why it is a one sample test. And we require to check whether the proportion of satisfied customers is same as the national average of 85%. Now you see over here, we see that it is apparently evident that 400 out of 500. Now this certainly is 80% that any of us can easily calculate, but apparently is it possible that this particular sample they actually belong to this population wherein 85% is the average level of satisfaction? So that is what we are trying to statistically prove or disprove. So which is why you have the null hypothesis, which is H0, which says P is equal to P0, or the sample proportion is equal to 85%, and the alternative hypothesis, which is the sample proportion is not equal to 85%, right? Okay. So alpha is the level of risk. Alpha level of risk and beta level of risk is what we have studied earlier. And alpha is equal to 0.05. This is a assumed value that we have taken upon. This is the risk that we are willing to take to achieve at this statistical solution, right? So alpha is 0.05 by default when we don't have any other value of alpha stated in the problem statement. So alpha is equal to 0.05. Now the point that we have the same given over here, it means that we are talking about what could be the opposite of not same? It is not equal to. So here we are talking about not equal to. Now the other alternative could have been is greater than or is less than, in which case we would not have the alternative hypothesis as not equal to. It would have been P greater than P0 or P less than P0, right? But the fact that we have put it in same, it means the alternative hypothesis is not equal to, which means this could be either greater than or it could be less than, which means we are talking about a two-tailed Z test that we are going for. See, for a Z test, there are certain criteria that are important. Number one is the kind of data sample that we're looking at. First of all, the number of data should be more than 30. So over here we are talking about 500 people over here. So certainly this qualifies for a Z test, right? So so the Z value should be between minus 1.96 to plus 1.96, which is the acceptance zone, and if it is not within this zone, then we can reject the hypothesis, the null hypothesis. So here we have a Z table, a positive Z table, because there could be a negative Z table also, that is also going to be shown now. Now the positive Z table, we read the plus 1.9 and we read the 0.6 and we come upon the value 0.975. Now this means that the probability that that if you have to take the sum of what is there on the left hand side plus 1.96 sigma on the right hand side of the standard normal curve, then you would you would be covering 97.5% probability that the data exists in that particular zone, in that particular area. It's only any number which is beyond 1.96 is only about 2.5%, right? So yeah, so 97.5% of data. Similarly, you have a negative side, a negative Z table also. In negative Z table also, similarly, you come upon the same solution, which is minus 1.96, wherein you have 25% of the data on the other side of the minus 1.96. So any value of Z lesser than minus 1.96, you have only 25% of, sorry, 2.5% of data. So if you look at both the sides, you have 2.5% on this side and you have 2.5% of on that side. That brings us to the need for a two-tailed test, or that brings us to what a two-tailed test requirement would be. So we have a standard normal curve over here. A standard normal curve is one wherein we have the mean, which is 0, as well as the standard deviation, which is 1, right? So for alpha is equal to 0.5, the value of Z, which is less than minus 1.96 or which is more than 1.96, is what is covered in the risk zone, which is, we're talking about this particular zone. Z is more than 1.96 or Z is less than 1.96. Only if any of these two conditions are satisfied, in that case we can reject the null hypothesis. If the value of Z that we obtain through the calculation falls over here, then we require to accept the null hypothesis. So this is the right tail distribution over here. Now in this particular value of Z equal to 1.645, we have 5% of the data which is on this side, which means all values from the negative to the positive end of Z equal to, till Z equal to 1.645, we have 95% of the data. This we would require to do if we were doing a one-tailed test. But since we are not doing a one-tailed test, we are doing a two-tailed test over here, because we could only check whether it is equal to or it is not equal to. The alternative hypothesis is that P is not equal to P0, as simple as that. So which means it could be either greater than or less than. So this particular part has 2.5% of the data, and this particular part has 2.5% of the data. This part of the data which is there for two-tailed test over here is 95% of the data. Note the difference in Z values. Here Z value is 1.96, here Z value is 1.645. Proportion of the bank customers who were satisfied and those who were surveyed. So 500 people were surveyed, 400 were satisfied. So P hat, which is the proportion of this particular satisfied customers, this particular ratio is 0.8, 400 by 500 equal to 0.8 or 80%. So now we can compute the equation by plugging in calculated values and the given values. Z observed equal to P hat minus P0 divided by root over of P0 into 1 minus P0 by N. So this 1 minus P0, it is also called Q0 sometimes for the ease of remembering. So if you plug in the values, you have P hat, which is 0.8, and P0, the national average that we have, by square root of 0.8 into 0.2. 0.2 because it is 1 minus 1 minus 0.8 is 0.2 by 500, so equal to minus 2.795. So minus 2.795, since it is less than 1.96, we require to reject the null hypothesis. What was the null hypothesis? That both the proportions are equal, which is P0 equal to P hat. So we require to reject that particular null hypothesis. See, now this is the particular limit between 1.96 and plus and minus 1.9, plus 1.96 and minus 1.96. The data, if it lies, it is in the acceptance zone. But if it lies within the other part of it, which is less than minus 1.96, or if it is more than plus 1.96, then it is in the rejection zone, which is we require to reject the null hypothesis. This is the value that you have got over here, which is minus 2.795. This is the this is of course in the rejection zone, so we require to reject the null hypothesis. Two sample proportion test. Two sample proportion test is a hypothesis test to compare two proportions to one another. And what is important is that these two proportions are of different data. They are not from, so they are from two different populations, not from the same population. So hypothesis, which is the null hypothesis, that is normally there is P1 is equal to P2, which is proportion 1 equal to proportion 2, and alternative hypothesis is it could be P1 not equal to P2. It could also, you could have a P1 is greater than P2 or P1 is less than P2, depending on how the question has been framed. Okay. The two proportions there. Here is a solved problem. The Six Sigma project lead wants to compare bank A staff, bank A. So this is your first proportion, right? Bank A's customer, I'm sorry, satisfaction rating with bank B. So here you have two separate customer satisfaction ratings over here. A random survey was conducted within each bank's customer, and the survey resulted in the following. All right, what happened is we found that in bank A, out of 500 customers who were surveyed, 400 were satisfied, and in bank B, out of 700 customers surveyed, 300 were satisfied. The summary is the Six Sigma project lead performs two proportion tests to determine whether the proportion of satisfied customer is same between the banks with 90% confidence interval level. So this is what we are talking about. The previous example, we didn't have this confidence interval level given to us. We had to assume it as a 95% confidence interval level. But here we are talking about 90% confidence level. I'm sorry, not confidence interval. We are talking about confidence level. Okay, so H0, which is your null hypothesis, states P1 is equal to P2, which means both the bank customers have equal satisfaction. Bank A's proportion is equal to bank B's proportion. And the alternative hypothesis, of course, is in this case, no, it is not. P1 is not equal to P2, or bank A's proportion is not equal to bank B's proportion. Okay, so we have alpha, which we know is the level of risk that we are taking. or the probability of an event not happening is 0.1. That's because the confidence interval, the confidence level is 90%. That's why alpha has been reduced to be 0.1. For this example, we'll use the following formula. Z1 minus alpha by 2 is equal to P1 minus P2 by square root of P1 into 1 minus P1 by N1 plus P2 into 1 minus P2 by N2. How to calculate? The pretty simple. P1 and P2 are proportions. P1 of the 500 people sampled, 400 were satisfied. So P1 equal to 400 by 500 equal to 0.8 for bank B. P2 equal to 300 by 700 is equal to 0.428. Therefore, when we plug in these values of P1 and P2 into Z1 minus alpha by 2, we get 14.374. That is the value that we get. So the confidence interval, the confidence level of 90% given means alpha equal to 0.1. So Z1 minus alpha by 2 equal to Z 0.95 equal to 1.65, which we can make out from Z table, which we'll be discussing in the next slide actually. Okay. So 1.6. We look at the Z value over here. The Z value for 1.65 is 0.95, which means 95.053% of the data or the area under the curve is on the left hand side of 1.65 as far as the standard normal curve is concerned. So when compared to 1.65, 14.37, which is our outcome that we found, the Z value that we found, it's much larger. So we can reject the null hypothesis. Yeah. So we reject the null hypothesis, saying that the customer satisfaction levels are not same for both the banks. So now if you look at this, this is a two-tailed distribution wherein we require to consider both the ends of the tail as far as the probability is concerned. Now we had taken alpha value as point as 0.1. The confidence was 90%. Alpha was 0.1. So which means 0.5 is over this side and 0.5 is over, sorry, 0.05 is over this side and 0.05 is over this side. So that means that 90% of the area under the curve is greater than minus 1.645 and it is less than plus 1.645. So that is 90%, and these two together is 10%. Over here what it's saying is the Z value found is 14.37. Where is that? Here you have till 3. 14 would somewhere be pretty far. So it certainly we can reject it. It is in the rejection zone. Anything which is on this side is in the rejection zone, or this side it is in the rejection zone. Okay? So we can easily say that the null hypothesis can be rejected. So customer satisfaction level are certainly not same for both the banks. Okay, the same thing when we give an input of the input in the Minitab software, we get the following outcome. Right? So herein we have the sample proportions which are given over here. The P1 and the P2. This is the P1 and the P2 that we have got. Now, interesting is when you talk about estimation of difference, it is simply the difference between these two. It is the estimate of difference. Now, the P value, the probability value that is much less than 0.1. We were looking at 0.1 as the probability value. Only if it is greater than that, we were about to accept the null hypothesis. But if it is less than 0.1, then we require to reject the null hypothesis, right? So the confidence interval is also found out using the software. It is between the estimated difference is between this value and this value, between 0.328 to 0.414 is the confidence interval in which the difference in satisfaction between both the banks are likely